So welcome to another edition of the Finite Element Seminar at Lawrence Livermore National Lab. Thank you for joining us. Today it's my pleasure to introduce Rob Falgout, who is going to tell us about the new advances in hypre 3.0 that just came out recently. Rob got his degree from the University of Virginia and joined the lab almost 35 years ago. Is that right? Wow.
That's 34.
34. As you probably know him from being the project lead for Hyper, but he's done other things. He's worked on the PowerFlow project. He's leading the efforts in parallel time integration, algebraic project. Won a lot of awards. He's distinguished member of the technical staff, SAM fellow, and currently is the SAM activity group on supercomputing career prize awardee. But today he's gonna go into the nitty gritty of software and hyper. So looking forward to that. Floor is yours. Thanks, Rob, for agreeing to present.
Hey, thanks, Sanyo. Thanks for the introduction and the invitation. So as Sanyo said, yeah, today's going to be talking about basically hypre 3.0, the new release that came out. And I'll be focusing on the two main additions that we made to this new release. So I won't tell you everything about the new release, but I'll tell you these two. I'll go into details about mixed precision and the semi-structured updates, and I'll do that in reverse order. I'll start with semi-structured, and then the second half, the last part of the talk will be about mixed precision. So here are the team members. What I'm going to present today was not just done by me, obviously. It was done by the whole team, and they deserve a lot of credit. Okay. I won't tell you what multigrid is, but just a reminder about hyper. One of the main things we focus on is developing multigrid methods. So that's the main, one of the main features of the library. The reason is because we're interested in solving really large problems, and they have this O of n scalability potential. There are many algorithms. I'll describe a couple today as I go through the new features. And yeah. Okay, another unique feature of the hyper library is these linear system interfaces. We call them conceptual linear system interfaces. And this little diagram sort of illustrates how it works. Across the top, we've got the interfaces themselves, and they're just ways of describing your linear system to the code. So on the right, for example, is the standard linear algebraic way where you'd say row I, comma j, column J has coefficient blah. All the way on the left is what I would call a structured interface. Here you might have grids, structured grids, and you describe your linear system in terms of stencils. And then in between is what we call semi-structured. So I'll be talking a lot about this left part today. The reason this is useful is because if you provide extra information about structure, then you can store things differently in something that's more native and takes advantage of structure, and write algorithms that also take advantage of structure. At the same time, because this is just an interface, we could build a more unstructured data structure under the hood and use a more general method such as algebraic multigrid. And that just, you still have the same interface for describing your linear system. You just switch flip a couple of knobs, and you get a different storage object type, as we call it, out, and then you can use different solvers. An example of a semi-structured grid is kind of shown here. It's a block structured thing. You can see each one of these 5 parts has structure in it in the normal Cartesian way. And you can describe the couplings within a part in terms of stencils. And then, of course, because these things are coupled together, you have to do something between the part boundaries. And that's why it's semi-structured, not just structured. And I'll say more about that in the next slide, several slides. Okay, so I'll start with what we had in hyper before hyper 3.0. And we had 3 main sort of underlying data storage objects or matrix objects. One was a struct matrix, and this image on the right is for the struct matrix. And it's composed out of what we call a grid. And for us, a grid is a union of boxes on a Cartesian index space. So a box is described by its lower and upper corner. And then on top of that grid, you have a stencil, which is a non-zero pattern, basically, for your operator and for a row of your operator that describes how data on this grid is coupled to its neighbors. And then, of course, along with this stencil, which is just giving you some structured information, you need the actual data itself. So we have an array of data, and that can vary across the grid. So the stencil is not constant coefficient. It wouldn't necessarily be like a 4 minus 1 5-point stencil everywhere. Those coefficients can vary, but they can also be constant in the code. We have a way of storing much less data and then designing our algorithms to use that data in an efficient way. So that's the structured part of the structured matrix. We also have a general compressed sparse row matrix, parallel compressed sparse row matrix. It's composed out of two serial compressed sparse row matrix, one for the diagonal block that couples state unknowns on the processor with itself, and then the off-diagonal part couples to off-diagonal data. And then the semi-structured matrix is a combination of the two. So semi-structured grids can look like the things on the right. I showed you the block structured one already. You can have structured adaptive mesh refinement as well, and things like overset grids. So you can be pretty complicated scenarios that you have. Okay, so one of the reasons for this release is that previously we had some limitations in what we could do in the semi-structured code. So both, I'll start at the top here, and here's a picture from the previous slide. And we had, for both structured and semi-structured matrices, we required that they had to be square in the previous code. And so that meant that, well, and this is just a reminder of how this works. You know, struct matrix, as I just said, is a stencil applied to a single grid. And the semi-struct is a combination. In fact, it's a sum of matrices of structured type and then unstructured with the par CSR. But because things had to be square, the matrix vector multiply was only for square matrices. And we also didn't even have a general matrix multiply routine in the code. And of course, these kinds of matrix vector and matrix type kernels are really important for designing and implementing solvers. So this has limited what we could do in the code before. Now, we did have multigrid solvers in the structured grid case. Two of them are listed here. SMG is Schaefer multigrid. It's not actually semi-coarsening, it's coarsening multigrid. And PFMG, but they are both semi-coarsening methods. If this is your grid, you take every other point in one direction, and that gives you a semi-coarsening pattern. One of them is very robust. SMG is very robust, but it's very expensive. And the other is a little less robust, but it's much more efficient. And I'll say more about PFMG. It'll come up again in a later context. But in order to implement this, things like interpolation and restriction, which correspond to multiplication of rectangular matrices, had to be implemented by hand. And they were also hard-coded for very specific stencil cases. So it wasn't very general code. It was written specifically for these solvers, and it made it difficult to experiment with and extend the solvers to do different things. And in particular, it made it difficult to implement multigrid solvers in the semi-structured case. So this semi-structured idea came about and was even implemented in like the early 2000s, 2002, 2003 timeframe. And we had the idea of writing multigrid methods that were semi-structured multigrid methods way back when, but we didn't have the tools to do it. So it kind of sat around as an idea for a very long time. And what we had up until just recently was very limited support. We didn't really have multigrid methods. We had something where you basically use this splitting up here, and you could apply SMG or PFMG to this part of the problem, and have an iterative method that's sort of built in that way. So anyway, this motivates what we did with the overhaul of the semi-structured code in hypre 3.0. And this is sort of an outline of what we did. Basically, we extended the matrix vector class beyond just using square matrices. So, the matvec does rectangular matrices as well. The implementation still supports both variable and constant coefficients in the matrix and combinations thereof. We're still based on stencils, but now we have to change what it means to be a stencil. This was a big part of this implementation, is how do we even define what it means to be a stencil-based rectangular matrix. And there are advantages of this. I've already alluded to a lot of these. It simplifies implementation. You can reuse a lot of kernels, and code optimization can also be isolated to a few kernels, but it also makes it trickier because these are now general kernels as opposed to very specific ones that were written for individual algorithms. And then we can extend this now to implement methods in the semi-structured case. And I'll tell you a little bit about a new solver that's also available in the release for the first time, this semi-structured AMG algorithm. Just historically a little bit, the redesign that is now in hypre 3.0 really started more than a decade ago, and we've been working sort of on and off on it. So it's been a long process, to say the least, but it's nice that it's actually in the code and being used in useful ways now. Another point I wanted to make, in case you hadn't noticed, is that this is the first major release we've done in almost 19 years. So we had hypre 2 point something for a really long time, until just this past September. Okay, so that's kind of an overview. Now what I'm going to do is dive into the details a little more about what happened and what we did. So starting with extending to rectangular matrices, okay? So basically, I mentioned this already. Now a matrix has both a domain and a range grid. So it has two different grids. One it computes on, and one it maps to put the result. And we had a bunch of different iterations on this as we were writing the code. And what we ended up in the end was defining this domain and range grid in terms of a common base grid. So basically, each one of these grids here is a coarsening of some common base grid, okay? And that ended up being very useful to do. So now when you have a stencil, you have to think about which index space it actually operates on. That'll become more clear when I do the example down at the below. So there's a concept of a stencil grid. Right now, it's one of these two, the domain or the range, whichever one is the finer of the two. But we'll probably be generalizing that in the future for a variety of reasons. And then we have another restriction about how these matrices can be defined. These stencil-based matrices can be defined, and we have to be able to represent the stencil in a compact way. I call it a range stencil here, which is really hard to explain, but you'll get a sense for what I mean down here in the example. So let's do this example real quick. Thinking about interpolation in this PFMG algorithm. So let's look at the pictures first. On the left is a fine grid. And then if we semi-coarsen in just the x direction, the darker bands here would correspond to what the coarse grid is. So I get this coarse grid based on that coarsening pattern. And then the way we do interpolation in PFMG is just two-point interpolation. So if by doing this coarsening, this is AMG terminology, we've now separated the points in the fine grid into two different types of sets. Normally we call them C points and F points. So the C points are the dark regions here, and the F points are the light regions. So if I'm at an F point to do interpolation, like at the 3,3 point, I take some sort of combination of values from the left and the right, and I put the result here on the fine grid at 3,3. If, however, I am at a C point on the fine grid, then I just multiply the coarse grid value by 1 and put it on the fine grid at the C point location. So from a notation wise, we can represent this as two stencils here in the second line here. The left one is when we apply the stencil and put the result at a find point on the range grid. And the right one is when we apply a stencil and put it at the a course point in the range grid. And the reason I've written it as two different stencils here, because these are more like what you would normally have in a stencil. Everywhere there's an asterisk here, there's no coefficient. So this is a 2-point stencil. It represents a row in the matrix P that only has two coefficients in it, two non-zero coefficients in it. And then the second stencil, again, it only has one non-zero coefficient in this case, and it's always a 1 in this case. And it represents those rows in interpolation that only have a single 1 in them. So P is really a sum of these two more standard stencils. And what we meant up here by one of the limitations about either you have to store the matrix itself as a single range stencil or its transpose. In this particular case for interpolation, if you write its transpose, you only get one of these stencils. You only need one stencil to explain it in this decomposition here. And that's important for the way we store things and do things internally in the code. Okay. And just a note real quick before I move on to the next slide. This is a stencil here on the right for the course grid operator. And I've for a course grid operator, here it's 9-point. And that would be applied on this course grid. Okay. So this first slide will be about MatFEC, and the next two will be about matrix-matrix multiply. So one of the things in the MatFEC that we've also done is we've always had a notion of ghost zones and hyper, and this is an extra layer of space in the data structure where you can put information from neighboring processors to, in a communication phase, and so that you can then do your computations really efficiently locally. But deciding how many ghost layers you need a priori, which is what we had to do in the previous implementation, is quite difficult because it really depends on the algorithm and algorithms internally that are going to be used and what they do. So here's kind of a simple example of something that happens in just a multigrid method. It's all in 1D here. So in the blue box above, think of this as just a piece of an index space on the fine grid. And we've got some boxes here that describe the data on this processor that lives on this processor for a vector X on the fine grid, okay? And no, actually, it's not a vector X that lives on the fine grid. This is just for a vector on the fine grid. And on the coarse grid is then you take every other grid point, and then and you end up with some boxes. Some of them drop out, like this 35 disappears entirely when you coarse them. And so you have this grid here. Okay. So now let's think about multiplying interpolation time. This vector X now, think about it living on the coarse grid. So we have two different kinds of operations we might want to do. We might want to multiply it by interpolation to map information to a fine grid, or we might multiply it by the coarse grid operator itself, and where it just stays on the coarse grid. And so to do that, you need to add some ghost zones. And that's what this lighter region is sort of indicating. In the case of multiplying P times X, your data space with the extra ghost zones looks like this. So you still have 6 boxes, but they're a little bit larger than the ones we start out with on the fine grid. And for multiplying by AC, again, we have to do the same thing. It's a little more clear here. You know, look at this box here. I've added a ghost zone to the left and the right, and that's kind of typical for a 3-point stencil. You have one ghost zone to the left and the right. But the main thing to notice here is we're operating on the same vector X. And the data space for that vector looks different. Here you've got 6 boxes of different sizes, and here you've got 4. And so if you want to prevent, when you're doing P times X and then multiplying later times the coarse grid, if you want to prevent doing a bunch of copies and resizing of data, you kind of have to take a union of these two ideas together and store store X so that it can support both types of operations. And so this is one example. This can get very complicated in an algorithm. And one of the things we've done to help developers is provide some tools where these things can be all computed sort of automatically, and we can say whether or not we want it to, we want this resizing of a vector to sort of stick and stick around so that we can compensate for different kinds of operations on that vector, et cetera. And then by doing this, we can really minimize reallocating and copying data and things like that. So this is an important tool that developers have. So that was MatVec. For matrix multiply, we have to build a matrix after you do the product that is also represented. That's also a stencil matrix, so it needs to have a stencil representation. So there's some stencil algebra that has to be done up front. And the way this works is kind of explained here quickly. If I'm multiplying two matrices A times B, what I mean by stencil here is you take a row of A times B and represent it as a vector. And that vector is equivalent to taking the transpose of B times a row of A represented as a vector. And this little identity here is how we write a little section of code that does a bunch of stencil algebra. And out pops, if you multiply three matrices together, you'll get a representation for what its non-zero stencil is, where each one of these stencil coefficients is defined as a sum of products of coefficients from the stencils A, B, and C. And all the details about what the subscripts and superscripts are all stored in this little code. And then we use that to then do the real multiply on real matrices later. So this is kind of a preliminary step. And during this process, we can figure out which of these coefficients can be constant, which ones don't have to be, etc. Some other things we do in the code, we only assume that we have two data spaces. So think a find space and a course space for doing interpolation restriction or RAP or these kinds of operations. Pretty much all of the operations we need in Hyper only really need two. This allows us internally to limit our internal box loop structure to only have three little data spaces in it, which is nice. We again compute necessary go zones automatically. We do some aggregation of communication. And then in order to mix the constant and the variable coefficient types of matrices together, we have a little tricky masking thing we do that I'll explain now. So a kernel looks like a sum of a bunch of these triples for three matrices multiplied by each other. And what we do is we take each one of these little triples and we write it as a coefficient, a constant coefficient, alpha, times three variable coefficients. And this alpha is what has the constant coefficients in them if we have constant coefficients in A, B, or C. So in particular, if all three coefficients A, B, and C are variable, this is just a 1. But if A, B, or C is constant, we multiply them together and we put the product in alpha. Okay. And then the other thing we do is then in the case of constant coefficients, say the first one, A, is a constant coefficient number. What we do is in this V1 place, we put a mask. So it's a vector that's either a 0 or a 1. And this helps us to know whether we're on or off the grid, which is really important to for getting the right answer. So everything in the kernel looks like something like products and sums of these kinds of things here. And we have lots of different cases we have to take care of. Some of this data might live on a find space, some on a course space. So we get different combinations of these things. We might have find, or find course, or find course, or whatever. And we need to be able to handle all those cases, and that's all in the code. We can also take advantage of the fact that you might have structured matrices, and we'll only do half of the computations as necessary. Okay, and then in the kernels themselves, we have sort of two ways of optimizing. One works well in CPUs, the other works well in GPUs. In the CPU case, we do sort of standard loop unrolling where you compute a single coefficient by adding as many of these triples together as possible in one line of code. What works better on GPUs is if we compute a bunch of coefficients and contributions to them all at once. And this allows us to reduce the number of kernel launches. And so this seems to be a better way to go about on the GPUs. Okay, performance. This is kind of some quick results on a CPU for PFMG. And it's comparing to the main branch. So it was really important, obviously, we're doing all this generalization and writing these tools, but we want our algorithms in the end that use the tools to be as efficient as they were to begin with. And we've done that. And it took a lot of sort of tricky stuff in the inner kernels, but it works. And this is just showing that over a 3 or 4 month period, we were working on these optimizations, and whereas in the original code, we didn't care about the optimization. We were just trying to get correctness, and we made some pretty significant improvements. The plots on the right are showing some results. On the bottom, so this is for a single node. So it's 56 cores, and we're just increasing the size of the problem. And this is showing the slowdown relative to master of the different phases of the algorithm. So the solid one is total time. You can see that's less than 1, so the slowdown is actually a speed up. The only thing that really slows down in the new code is the setup phase, and we'd like to do some more work to improve this. But the reason this doesn't really make much difference in the end is because the setup phase is for PFMG is such a small component of the overall time that's involved here, as seen in the top, which is just plotting pure time. We also did something similar for GPUs and got in similar improvements in the new hypre 3.0 version versus the master case. Same or better, slightly. In neither case, it's dramatic improvements. Okay, and I think this might be this is the final part of this semi-structured, and it's about the new solver SSAMG. So this is a solver that is composed out of the PFMG and BoomerAMG solvers in Hyper. So here's a picture on the right of a bunch of different structured parts glued together across these boundaries in some, potentially arbitrary way. And basically the way the algorithm works is within a part, we do semi-coarsening as we do a PFMG. So you see the semi-coarsening is not necessarily in the same direction in each of the parts. And then within the part, we do 2-point interpolation like we normally do. And currently in the code, we don't do any interpolation across the part boundaries. So our interpolation operator is not a sum of two things, it's just interpolation within a part. That's what's in the code right now. And what I'll tell you about with the results on the next few slides. We would like to have this generalized so that there's an unstructured component that allows us to interpolate across boundaries that will improve convergence. We've seen indications that it can dramatically improve convergence. So here, for example, one case is reducing 20 iterations to 7, which is pretty significant. But what we have in the code right now needs a lot of work from an optimization standpoint. So this is still work in progress. And this kind of shows what happens when you have the full-blown case. And this is what prevented us from implementing this a long time ago. You can see you've got lots of cross products here involving structured and unstructured matrices. And it just seemed like a big mess to do all this, especially for a very specific solver instead of what we have now, which has the more general matrix support that we need. So anyway, this is SSAMG. And one final comment. The way we do this is we coarsen, as I showed here, construct a coarse grid operator, but then at some point in the algorithm, this is something that is a parameter that can be set. We switch to doing BoomerAMG entirely. So you come down the V cycle, in this semi-structured way, and at some point you switch to fully unstructured. Okay, so I'll show results, 3 results. They all live on a cube shown here with 4 parts. They have a 7-point stencil that's anisotropic in X, Y, or Z and combinations thereof. This shows how the minimal processor decomposition is, and here's a decomposition across 32 processors. And these results actually exist in a paper from 2023. But what I'm going to show you is an update to that, and the performance is a little bit better, but it's qualitatively the conclusions are the same. So the first is where we have anisotropy in the X direction, all 4 parts here, shown here on the right. And really, so here we have setup, solve, and then this is convergence. So the left 2 plot time relative to number of MPI tasks, and the right is the number of iterations. And really look at the solid red and the solid purple. That's the best performing SSAMG setup versus BoomerAMG. And the main thing to see here is that in the setup phase, we get a significant improvement in time. And so overall, we get an improvement in time as well. And convergence solve phase is similar to AMG. It's not faster. We'd like it to be faster. But that's going to take a little bit more work. Same kind of situation. Now we have anisotropy in X on the left and anisotropy in Y on the right. And the conclusions are kind of the same. Again, we get about a 7 times speed up in setup. Solve phase are similar times between the 2 methods. And then the last, I have X bottom left corner, Y top right corner, and these other corners are in the Z direction. And again, similar kind of conclusions. Okay, so that's the semi-structured part. And now I'm going to switch to the last part, which is about the mixed precision things we've added. This is the other big component that we have now in hypre 3.0. It's something we've also worked on, I don't know, maybe 4 years or something. I'm not exactly sure. We started working on this a while back. And obviously the reasons are the reasons that a lot of other people are doing mixed precision in their codes. The hardware is has good support for low precision computing. So we'd like to take advantage of that. The other thing is limiting bandwidth so that we can put more things on the GPU. You know, the more computations you could put on a GPU, the better off you are typically. Okay, so we had several goals and several features that we added, and this is kind of a summary of that. To start off, let me say what my terminology is. When I say multi-precision, that's basically a solver function or feature that uses 1 precision at a time. So Hyper, even before hypre 3.0, was actually a multi-precision library where that precision was determined at compile time. Mixed precision, on the other hand, is a solver function or feature that has different precisions used at the same time simultaneously. So that's how I'll separate that terminology. And what we did in this release of hypre 3.0 is the 2 main things we wanted to achieve. First was to do the multi-precision part at runtime. And the second was also to have actual mixed precision solvers that we provide so that we can get some improvement, get faster and more memory efficient solvers in the code. Okay, so some features. You can configure Hyper with the mixed precision turned on, and you don't have to change encode. It should run as before without any modifications. All of the other thing we wanted to do was make all of the compile time precisions we had before available at runtime now, so you can actually switch between them at runtime. And that's what this next line is about. Something we're doing in the future, and it isn't in there yet, is assign precision to objects like matrices, and then have things like matvec automatically determine what precision is ideal for doing the matvec, given the precision of the matrices and the vectors that are passed in, for example. And then we've added some mixed precision solvers in hypre 3.0, and we have more to come, and I'll say more about that too. Okay, the first part is about providing runtime precision. So again, I mentioned before, you could do this in Hyper at compile time before by just configuring it to be, say, single precision, and that all worked already. Now you to use mixed precision, you just have to use one of these two configuration options, in either the auto tools or the CMake situation. As I said, this doesn't change in user code. And then the next slide will give you more idea about what's available now when you actually configure things with mixed precision and what you can do. So when you configure with mixed precision, you have several things that are available to you that weren't before. So I'll use this term foo to represent any function in Hyper. So for example, Hyper PCG solve, all of it's going to be represented as foo here. And one of the things you get when you turn on mixed precision or configure with mixed precisions, you get each of the fixed precisions available to you with these symbol names. So foo underscore FLT, foo underscore double, etc. And so as a user, you can call these directly. And if you called foo underscore FLT, you would get a single precision version of whatever foo was. The prototype for this function here is the same as before, except that the things like hyperreal, all the real types basically map to whatever the underlying C type needs to be. So in the case of foo FLT, it's float. We also still provide the symbol foo as it was originally in the code. But now, since it has to handle, now it handles any precision sort of simultaneously. And that precision is determined by a global variable that you can set through this function here. So you can actually call this set global precision, and it will set a global precision. And then when you call foo, the precision that will be used is going to be determined by this precision that was set here. Now, for this function, the prototype is a little different now, because now the prototype, especially for the real either scalars or vectors, it has to support multiple precisions all with the same prototype. So the way we do it, we're doing that currently in the code, is everything that was a hyperreal in the original case is now a long double. So it's big enough to fit any of the doubles without losing precision, any of the real values without losing any precision. And then everything that's an array of reals becomes void star. And here again, we want to pointer to some data that can be of any type, any real type. And so these are the two ways we can do that. This does not cause any compile complaints. It's valid C code. There may be a compiler at some point that might give some warnings. It's been looking pretty good so far. And with this prototype, you don't have to do any extra casting or any of these kinds of things generally, which means your code can stay the way it is. One other thing we provide in addition to these three symbols at the top is a new symbol called foo underscore pre for precision. And the arguments for this are the same as the original function, except we add this extra precision argument up front. And this is a really useful function when you're writing mixed precision code. It just allows you to write cleaner code in a lot of ways, instead of calling these specific functions up here and then having lots of case statements all over the place. You can manage things a little bit nicer by using these functions. And we do use this internally in some of our mixed precision code. Okay. We don't have really good example drivers to illustrate this yet. That's something that's in the works. But if you wanted to, you could look at a test driver we have, our struct driver. Because what we did here is we added this command line dash precision argument that does this runtime switching. And it allows, this is one of the ways we test to make sure everything's working right. We can run all of our regression tests that we had before and just add this extra precision argument, for example, and we should get the same results as we did when we ran things in the statically compiled float or double or long double way. So here's an example command line where you say precision 0, 0 here on the command line means single precision. So you get a residual at the end that's like 10 to the minus 7. And if you do it in double, you get 10 to the minus 16. So you can actually see this on the command line pretty quickly with our existing test driver. As far as code changes, and this is one of the reasons we did this, we wanted to get a sense for what users would have to do to actually use mixed precision or use this runtime multi-precision option. There's two things. You have to have this call where you set the global precision. That's one line of code. And then one thing that we found useful was to write utility routines that do copies between different data types for us. So for example, this data copy to multi-precision takes a double array of values, which was already sitting there in the driver, and copies it to this void star pointer of host values that can be whatever type, that is whatever type is set currently in this global precision variable. So this was very useful. It meant we didn't have to change a lot of codes in this struct driver to get this behavior out. So anyway, and example drivers will come in the future, and that'll be probably better for users to look at. So we also have some mixed precision solvers available. The only one we have right now, the only ones we have right now are basically lower precision preconditioners of higher precision Krylov methods. Here again, we tried to do this in such a way that it doesn't change much user code. In fact, you really only have to add this set precon matrix call to give the Krylov solver the lower precision matrix that's needed for the preconditioner. And we also have a few utilities that helps you construct this lower precision matrix. You could do it yourself using the standard tools, but we also have a few that do convert for you. And then I've got showing some results here. This is speed up versus number of cores for 3 different preconditioned CG methods. One AMG, so this is with the parse CSR storage, and then the other is with the struct object type. And you can see we get speed ups like 30% for AMG and maybe 60% or so for SMG. And anyway, you can get some decent speed ups. This is all on the CPU. We currently don't have this solver available or even support for mixed precision on GPUs. That is already in progress. We have a draft PR that we're working on that should come soon. Another thing we have, and I'll show you the results on the next slide, is an implementation of BoomerAMG where you can change the precision on different levels. And that will be coming soon as well. Yeah. So actually, this is the AMG, mixed precision AMG. So as I said, you get different precision with different levels. So what does that mean for the algorithm? So in the setup phase, you have to create this. One of the things that has to happen is the code has to create a lower precision matrix to use on the levels where you have lower precision. And in the solve phase, you have to do some conversions of residual and error vectors when you're mapping between coarse fine levels that have different precisions. So this is extra things that have to happen in the code. The API is also different. If you want to use this, you have to call BoomerAMG solve, for example, with the _MP after it for mixed precision. But otherwise, the parameters and everything else are the same. You just they have different names here. Ulrika did the work here, and one of the major challenges she had was dealing with the AMG data structure internally, because things that are scalars, when you try to reuse that structure on a level where you have lower precision, suddenly the structure changes size, which is difficult to deal with. So it took a while to sort this out and get things working, but it's working, and it's not ready to submit or commit yet to master, but that's in progress and should happen soon. And this is showing some speed up similar to on the previous slide. comparing to just standard double precision AMG CG. And really, I would only look at the blue. So the orange line is using single precision AMG BCG. And the dark blue line, the one that's closest to it, is using a certain combination of lower precision on course levels. And the way the thing that works best is to take the earliest levels, level 1, 2, 3, for example, and make those lower precision. And that gives the best performance. Anyway, that's coming soon. Okay, I think this is the last slide. Yeah. Just wanted to say a little bit about how we achieve this in Hyper. So as you know, Hyper, the first release of Hyper was in '98, and at the time we decided not to do C++ because it was kind of early. We thought, and so everything was done in C. And so how do we add mixed precision support in the code? We basically use scripts quite a bit in auto code generation. So let's see, this is some detail. So for every symbol in the library, we actually have some special files where we keep lists of them. And then from a sort of a workflow perspective for developers, there's a couple of scripts you need to use. You run this MUP check script. Basically checks to make sure that all of the symbols that are in the library appear in one of these lists that they need to be in. The reason they need to be in these lists is because this is what we use to auto-generate wrapper code that's necessary to get the mixed precision and multi-precision capabilities. And then once you got everything in the right place, you just run this top-level script MUP_code, and it generates a whole bunch of code and header files, and we commit all that to the repo. So this is how developers work. And the way the build works when you're configuring with mixed precision is basically the code gets compiled 3 times, and each one of those, basically for each one of the precisions, single, double, or long double, and then there's one extra compile of all the auto-generated code that we did up here in the top part. And so this chart kind of shows you here's the 3 files that are special files, and it shows you which symbols are created with each of these builds here. So when you're building the single precision stuff, the foo_float symbols get generated. For double, float, double, and long double are generated basically in these first 3 compiles. And then we need to have a symbol for the original symbol foo that now supports mixed or multi-precision at runtime. And so this is the wrapper generated code. And in addition, there's this foo_pre code that is also wrapper code that is auto-generated to begin with. This shows an example of what this code looks like. And it simply just switches on the precision that gets passed in when you call this, that's the first argument of the pre function, foo_pre. You just do a switch and call the appropriate float, double, or long double based on the precision passed in. So, and this is all auto-generated. We don't have to, it's not something we have to do other than run a script. So that's kind of in a nutshell what is in this new release, Hyper 3.0. This is a summary of the 2 main parts. Do I need to say anything more here? I guess you can just read it. And I just wanted to show this is a team. These are the people responsible for everything I just talked about. And you probably know already, but you can get the code at GitHub sites, and we also have a lot of our publications at the Hyper site here too. With that, I'll stop and take any questions if you have them. I see there's a few things in the chat.
All right, thank you very much, Rob. We appreciate it. Yeah, so in the chat, Mike asked about what is the application for non-square matrices, and Victor answered it, but if you want to add to it.
Yeah, I think that's the answer, and that became clear, I'm sure, as the talk went on. It's mainly for us internally for writing algorithms.
Okay. All right. Other questions for Rob? Please feel free to raise your hand or just unmute and ask. Okay, I can ask one to get us started. In the multi-precision AMG, is it still the case that if is there any issue with positive definiteness? If we have an SPD operator, is the multi-precision BoomerAMG still positive definite?
I think the answer is yes. I don't see why it would not be. I don't know if there are any kind of IEEE rounding things that might cause problems, but I mean, that can be a problem anyway. Why do you think it might not be? Did you have a reason you asked that question?
Well, just because I've heard that people have issues with getting things that's supposed to be Hermitians are not. I was thinking about the rank of the interpolation matrices that may not be somehow. Once you change the range, it may turn a full column rank into non-full column. I don't know. I'm just guessing. That's why I'm asking.
Oh, I don't think so, but I mean, Ulrika would know for sure. I think the interpolation is constructed from the matrix at that precision to begin with. So, you know,
Okay.
if you've got a double precision matrix, you construct P based on that, and that will map between a lower order precision and the double precision case. And I think the conversion happens in precision between the vectors, basically.
Right.
But the construction of the interpolation, I think, is the same as it always has been. The code's the same.
Okay. So we have another question in the chat. Shu, how do you want to unmute and ask the question? Do you want me to read it?
Okay. Yeah. So hey, Rob, Shuhao here.
Hey, Shuhao.
Nice talk. I'm just curious, is there any plan to port hypre to CUDA, considering it's already C++? So
Oh no, we do have a CUDA implementation already. Yeah.
like I mean, not only to CUDA, but use it as a PyTorch extension.
I'm not
the last
sure what
part,
that
I have
means.
no plans to do anything like that, but
Okay, so
yeah.
yeah.
I mean, the CUDA part's all there.
Okay.
Yeah, that's already there. And you mentioned C++, and I said C earlier. To support GPUs, we needed to have some C++ in the code.
Okay.
So
yeah, so there is currently no plan to port it as a PyTorch extension, I assume? No.
No, there's no plan that I know of.
Sounds good. Thank you.
Shuhao, just for those of us that don't understand, what does it mean to be a what does it need to do to be a PyTorch extension?
Oh, so let me explain a bit. So by PyTorch extension, it's pretty much like you can. So it's PyTorch is like you can use. So for example, PyTorch is in Python, right? So in Python, you can call certain wrapper of C++ code. If you write it, if you wrap your CUDA code as an extension of PyTorch. So there are certain formality you need to follow, but it's not that bad because I use this AMG extension written by a Russian guy. But yeah, I'm just curious.
Okay, thanks. All right, other folks, please mute and ask. So Rob, what the goals for a lot of this mixed precision, of course, is lower precision GPUs. But are there people using hyper that want to go in the other direction have extended precision? Is it both ways, or is it really for lower synced
I
up?
haven't heard anybody want to go the other way. I mean, yeah, one of the issues we have with GPUs is that they don't have long double, for
Yeah,
example.
I know.
So that was a little bit of a wrinkle that we had to deal with. Yeah, no, I haven't heard anybody want to go extended precision. Seems like everybody's interested in the other way, but
Mike, you have another question you want to unmute?
so he's asking about AMGF. I actually don't know the availability of AMGF.
Well, I think he's really interested in elasticity type of problems.
Yeah. Have you read some of the semi-structured stuff on the elasticity problems? Because it seemed like it could help.
Right. But are you thinking about when you say S-struct? Are you?
Oh,
are you
I
thinking
meant
about
I
like an
just meant
SS?
I just meant the you have the structured version of hyper now that we can use, right? Where we can give it matrix structure, right?
You always could do that, but now we have more solvers.
Okay.
And there will be more in the future that take advantage of the structure. That's the main
Right.
thing you'll get here.
Right. Because we haven't tried it yet. I want to take advantage of that. So.
And we've also done only limited testing of the semi-struct solvers that we now have, especially like SSAMG, the one I mentioned.
Yeah.
We're kind of in the process of testing that out with other people's real problems.
Yeah.
And we're also extending it. So, there could be an SSAMGF at some point. Now we have the tools to do that.
Yeah. If you want, we can give you some matrices,
We're collecting matrices.
We just have to know what format.
That would be
Okay.
good. Maybe we can meet offline about and have yeah.
Thanks, Rob. Thanks.
All right. Thanks, Mike. Any other questions for Rob?
Yeah, so just to summarize real quick though, while we're waiting, if there's any other questions, part of this is to get some tools that will allow us to provide more solvers in the future. So, there's a lot of ideas we've wanted to implement for a long time that, now we have the tools to do that, and it should be easier for us to do. And so hopefully down the road, you'll see more things coming out of this as a result, which was always the hope. So.
Yeah. How did you decide to go to new major release? And why didn't you do it earlier?
When it takes more than a decade to rewrite a whole component of the code, we had, there were 1,000+ source code changes.
Yeah.
And a lot of it was non-trivial.
Yep.
So it just made sense.